Pro-micron presents the sensory tool holder spike. The following presentation will show you an example for how the spike will help you to truly understand your processes so you can make the right decisions and optimize them faster than ever before. In this case, a process to mill out a typical dog bone, 8 tool operations are carried out. First, helical interpolation to achieve the needed depth for the milling cutter. Second, spiral interpolation to remove as much material as possible. Third, trochoidal milling to achieve the rough shape of the dog bone. Interrupted by, fourth, a short linear interpolation to clear out the curve on the left. Afterwards, the cutter goes back to trochoidal milling to finish the left side. Thanks to the spike and the tool measurement software, we can see the development of the axial force, torque, and bending moment in real time. Moving to the right side of the part, we once again start with a helical interpolation, followed by a spiral interpolation, followed by trochoidal milling. The final step of this part is a linear interpolation along the whole dog bone to clear off the surface. And here we can see a drop of the bending moment to 0. This indicates that the cutter isn't cutting any material at this time. This is not what we want to happen here during the finishing pass. Alright, after the whole operation, we can export the data to the tool analyzer software, where we can see a sheer overwhelming amount of information. But if you know how to read the data, you will turn this information into knowledge. If we turn off the axial force and torque, we can clearly see the development of the bending moment. If we overlap the individual operations, we can see what the spike can show you about your processes after only one use. Now, of course, the question that comes to mind is what to do with all this information. Well, to be able to make the right decisions, you have to understand what is happening with the tool and how the forces are applied to it. To understand is the first step to improvement. For that, let's take a look at the linear interpolation finishing pass. As we can see, there are variable values of the bending moment, but they are to be expected since we are removing excess material. However, as we noticed before, there is a drop of the bending moment to 0 at this point. In this operation, this means that the tool isn't cutting anything except air, leaving an unfinished surface and incorrect dimensions. How does this happen? There was either a mistake in the program path during the final operation, or too much material was removed during the previous operation. Due to the correlation of time, force, and programming, we know that the drop happens here. The program path was correct. So let us take a look at the whole operation and see what we can find out. Operations 3 and 4 are responsible for shaping the dog bone on the left side. So let's take a closer look at those. Here we notice 1. A fairly uneven spread of the bending moment, and 2. These peaks. We call those peaks tool shocks, and they are very hard on the tool and cause it to wear out faster and possibly break. So you generally want to avoid those peaks in your bending moment and try to level the forces that are applied on the tool. Upon further investigation, we notice that these peaks appear when the machine is milling out the exact same spot where the bending moment drops to 0 during the finishing pass. So let's think about how or why these peaks might appear. One reason could be that the trochoidal milling operation left too much material behind that is now picked up. But that does not explain the drop in the finishing pass. The actual reason here, the operation with a programmed feeding rate of 315 inches per minute, the fastest the machine can go, is simply too fast for the machine to slow down and to change directions, causing the tool to cut into the material. To solve this problem, we decrease the feeding rate by 20%. That way, the machine is actually able to go along the programmed path. In addition, we double the step over to counter the increased time needed caused by the slower feeding rate. We run and measure the process again with the spike and the new parameters, and the result is this graph. Now let's compare it with the bending moment before the improvements were made. We can see that the peaks were reduced compared to the rest of the process. Removing these peaks, or tool shocks, is crucial to increase tool lifetime. On the other hand, due to doubling the step over, the overall bending moment increased by about 33%, which means that the tool will wear out faster. But for two reasons, this is not much of an issue. First, the overall process is more stable, controllable, and safe, since the bending moment stays at about the same level, and also stays below the level of the peaks from the first run, which the tool is capable of handling. Second, we reduced the time by 40%, and experience has shown that the savings from reduced process time are far higher than the cost for extra tools. With these new parameters, we're not only earning money thanks to a shorter process time, but we also get a more accurate part with better quality. If we look at the linear interpolation finishing pass after the changes done to operation 3 and 4, we can see that now the tool is always cutting material, so the surface and dimensions of the finished part are as they should be. Obviously, we can keep changing and refine the parameters to get even better results, but for now we have solved the most critical errors and we can already see great improvements which were only possible with the spike. So let's move on and take a look at what the sensory tool holder spike is also capable of showing you. Let's look at helical boring, a 3-axis operation with circular interpolation in X and Y and boring in Z-axis. Here we see the cutout data for the helical boring process. We can see that the peaks have about the double amount compared to the steady state. Those peaks indicate a non-stable process, and as operators, stability and safety are of high priority. But since the feeding rate for boring in Z-axis is limited by the geometry of the tool and already at the maximum amount, we're not going to alter this process. The peaks seen in the bending moment are significantly smaller compared to the rest of the process, and so are of no immediate concern to the tool or the process, but have to be kept in mind if the helical boring process gets altered with. Also, when stacking polar plots, we can see the instability during the peaks compared to the steady state. So there is a huge amount of data that would not be available without the spike. And it is with this information that you can truly understand your process, so you can make the improvements if necessary. Before we continue, let us have a look at the polar plot. How is it made and what does it mean? Since the sensory tool holder spike can measure the bending moment in X and Y axis, every dot represents the measurement of the resultant force applied on the tool. The coordinate system of the polar plot is turning with the tool holder, so it is possible to show, for example, the individual cutting edges of the tool, to visualize wear and tear, problems in the process, to help in tool development, or like in this case, to show how stable or unstable the process really is. Alright, let's move on to the final process that we'll look at in this video, the spiral interpolation. If we cut out the data of that operation, we get the following graphs. We can see significant amplitudes in the axial force and torque, and also a wobbling bending moment. What we can see here is the result that we are working on a 5-axis machine. That means the machine is not only able to move the tool in X, Y, and Z axis, but can also rotate the table in an A and B axis. What we can see here is the result of the table moving with each passing of the tool. Thanks to Spike, we know what's going on. Now we can increase the accuracy of the cut and decrease the time needed. So let's do that. Once again, we decrease the feeding rate about 20% and double the step over. We run and measure the process again with Spike and the new parameters, and the result is this graph. Comparing it with the graph before the changes were made, we notice 3 things. First, the amount of wobbles has decreased. Since we doubled the step over, we have to complete less rotations, therefore the table moves less often. Second, an increase in the bending moment about 33%, but also third, a reduction of the process time by 1.5 seconds. Looking at the polar plot, we can see not only the edges and the helix of the tool, but also differences in the amount of the bending moment, and is the result of a 2-degree difference in the helix. This does not only show you the capabilities of the spike, but if you are, for example, a tool developer, this can be a great benefit for your tool development. This video showcased just one example for how to use the sensory tool holder spike. And whether it's milling, boring, threading or grinding, every process is different and has its own peculiarities, and the spike can help you to pinpoint them. So hopefully this in-depth analysis showed you how the spike can help you to understand your processes and to change them to your liking. The sensory tool holder spike comes in a sturdy and portable aluminum case, complete with a receiver, the necessary software and charging station, other individual equipment to operate your sensory tool holder, and room for a notebook. Contact us today to get the most out of your machining processes.